This is CyberWise Tech. Don't forget to like, share, and subscribe.
Modern smart factories demand complete real time visibility into their operational technology assets. Yet, most manufacturing facilities struggle with fragmented inventories, manual spreadsheets, or active IT scanning tools that risk crashing legacy plant equipments. Welcome to CyberWise Tech, and in this briefing, we break down a battle tested architecture for non disruptive OT assets discovery, Purdue Model taxonomy, and enterprise CMDB ingestion, delivering complete asset intelligence without risking plant uptime. To understand why a traditional asset mapping fails on the factory floor, we must look at the fundamental conflict between enterprise IT and operational technology. Enterprise IT security prioritizes confidentiality and relies on active ICMP or TCP probes to scan networks. IT systems are built to handle frequent patches and restarts. On the other side, operational technology operates under the exact opposite priority. Availability and physical safety. Legacy PLCs, serial gateways, and level 1 controllers feature low bandwidth, low memory network stacks. When active IT vulnerability scanners probe these assets, the sudden packet volume causes buffer overflows, dropping critical control frames and tripping safety relays. Safe OT discovery requires a zero packet injection approach. Before deploying any discovery tools, you must establish a standardized asset taxonomy aligned with ISA IEC 62443 standard and the Purdue reference model. Assets are structured across four operational levels. At level 3 and 3.5, we manage site operations, MES, plant historians, and engineering workstations. At level 2, we establish supervisory control, including SCADA servers and operator HMIs. At level 1, we classify direct automation controllers, such as an asset discovery record is only useful if it captures operational context. To populate an enterprise CMDB, every configuration item must capture four layers of metadata. First is administrative data, establishing ownership, ID or tag numbers, serial numbers, and vendor details. Second, technical attributes, capturing MAC address, the fixed subnets, IP assignments, active firmware builds, and open ports. Third is ISA 95 context, mapping each device to its Purdue model, physical panel location, production line, and criticality class. And fourth, dependency, mapping how field controllers feed data upward into HMIs, SCADA nodes, and MES databases. Capturing these four layers transform a basic IP list into an authoritative operational record. To collect this data without risking planned downtime, we execute a three-tiered discovery methodology. Tier 1 is passive deep packet inspection. By configuring SPAN ports or installing inline network TAPs at core managed switches, passive OT monitoring appliances listen to raw network traffic. DPI decodes native industrial protocols such as Modbus TCP, Ethernet IP, and Profinet, capturing MAC addresses. Active IP pairs, firmware headers, and rack card slots with zero packet injection into live control loops. Passive monitoring captures talkative network devices, but complete coverage requires Tier 2 and Tier 3. Tier 2 uses safe native querying. During scheduled maintenance windows, targeted vendor native commands like CIP identity requests or Siemens S7 block reads are issued to pull exact backplane, slot details, and logic checksums. Tier 3 is the physical cabinet walkdown. Automation engineers inspect enclosures to map serial only devices, unmanaged switches, and standalone hardwares that do not communicate over Ethernet. This guarantees 100% asset coverage. Raw discovery data from passive applications or appliances or CSV audits must never be dumped directly into production databases. It must pass through an identification and reconciliation engine. The IRE normalizes vendor strings and enforces string matching rules to prevent duplicate records. Rule 1 matches on serial number plus vendor. Rule 2 matches on MAC address. Rule 3 uses IP address only as a tertiary fallback. This governance pipeline ensures that dynamic IP reassignment or maintenance swaps do not pollute platforms like ServiceNow, BMC Helix, or Device 42, or whichever platform you're using as your CMDB one. Once assets are reconciled in your CMDB, they are grouped into logical security zones based on operational function and risk profile. Adhering to ISA IEC 62443-3-2, communication paths between zones are explicitly defined as conduits. Establishing defined conduits allows your network and security teams to implement zero trust microsegmentation. Establishing a structured IT/OT CMDB architecture delivers three measurable business outcomes. First is you will see a reduction in your MTTR when a controller fails. Technician instantly retrieve exact firmware baselines, physical cabinet locations, and direct links to configuration backups, cutting recovery time from 12 hours to under 45 minutes. The second advantage you get is rapid vulnerability response. When 0-day CVE disclosures occur, security leads query the CMDB by vendor and firmware version to identify affected hardware immediately without manual plant audits. And third is CapEx lifecycle management. Tracking hardware end of life dates enables proactive 3-year capital expenditure planning for legacy hardware upgrades. Transitioning to a fully maintained OT CMDB follows a clear 4-step roadmap. Establish your Purdue taxonomy, standardize the 4 CDE layers, execute tier discovery, and activate your CMDB reconciliation engine. If your organization is modernizing smart factory infrastructure or preparing for an ISA 62443 audit, book an IT/OT architecture audit with our team at ACH Solutions. We will help you design a customized discovery roadmap and security architecture tailored for your plant floor. Thank you for watching. Be sure to subscribe to CyberWise Tech for more industrial cybersecurity frameworks.